Thank you, Professor Greenleaf. First of all, I'd like to advertise these books. They are on display for you guys, and we use them for our notes for FIOs. So maybe you'd like to look over them in the break or also find them in your libraries in your universities. Okay, so let's see what happens today. Overview. We're going to go over conormal distributions again. So we're going to review this. We're going to continue with non-degenerate phase functions. Then I'm going to talk a little bit about symplectic geometry and Lagrangians. At this point, we are ready to introduce the Fourier integral distributions. We're going to extend this to Fourier integral operators. We're going to see some estimates and then an application of FIOs in the seismic imaging. Okay? So let's start with the review of the conormal distributions from yesterday morning. So what do we have here? We have a manifold of dimension n. We have a submanifold of codimension k, so given by k defining functions with linear independent gradients. Then we have the conormal bundle, again defined yesterday, the set of points xc such that xc is tangent to, is orthogonal to the tangent space. So xc has the form theta j d phi j. Then we look at the distribution of this form. We have the phase function, the sum of theta j phi j, and a symbol, very simple symbol, Sm of 1, 0, again defined yesterday. And we define by Im of x and y the set of all the distributions of this form with for the conormal bundle n star of y. It was shown that the wavefront set of u is in the conormal bundle of y. And now if you look at the phase function, so whatever we have an exponential, we have a phase function here. This is a special phase function. This is a linear phase function in theta. Let's try to generalize this. So let's look at other phase functions. So first of all, what is a phase function? What do we call a phase function? So we have a smooth function x cross Rn, small x from the manifold x dimension n, theta from Rn, which is real. It has homogeneous of degree 1 in theta, and the gradient different than 0. So if phi satisfies this, then phi is a phase function. Now, this is a theorem which wasn't proved yesterday. We're going to prove it today. If we consider a symbol of order m and we form this distribution, very similar distribution like the conormal one, we have integral of e to the I phi a, then the wavefront set of u, the singularities, are in the set x dx phi such that d theta phi equal to 0. It's a very, very nice set, and we should get familiar with this very quickly. So we have x is the space variable, theta is the phase variable. So here we have x dx phi such that d theta phi equal to 0. This is a very important set. We're going to work a lot with this when you go to FIOs. So this was a condition of first order for the derivative. Let's add a second order condition. We go further here. We make phi non-degenerate. So we look at the critical set where d theta phi equal to 0. And we consider all these derivatives with respect to theta and their gradients. If they are linear independent, then phi is non-degenerate. So we add something on the phase function. And this will help us for the following. If it's non-degenerate, then this map is surjective, so we have the rank n. If it's non-degenerate, then the critical set is a smooth manifold, conic and closed, yeah, because phi is homogeneous of degree 1. If it's non-degenerate, then this map from x theta to x dx phi is an immersion, so d phi is injective. And also the image is a special manifold, a conic Lagrangian, which we're going to define later. And again, it's very important for the FIO setting, the conic Lagrangians. If this is the case, then phi is going to parameterize lambda phi, okay? So lambda phi, it's exactly this set, the image of h, x dx phi such d theta phi equal to 0. Okay, so let's prove the theorem from yesterday. We're going to sketch the proof. It's in the books I told you about. So let's remind the theorem. The wavefront set of this distribution is in lambda phi. So we're going to show that if a point is not in lambda phi, then the point is not in the wavefront set. So let's consider x0, x0, a point not in the lambda phi. We're going to show that using the definition of the wavefront set, again defined yesterday and I think on Tuesday also. We're going to show that if you consider a function C0 infinity, then the Fourier transform is rapidly decreasing. Okay, this means that it's not in the wavefront set. So calculation here, u, psi, Fourier transform, the phase function is phi of x theta minus x dot xc, a and psi. And now we're going to use integration by parts. Yeah, this is something we use all the time. We're going to find the differential operator, which leaves the exponential invariant. So L applied to I phi minus xc is the same. And this is given by the derivative with respect to xj. Then we have here d phi dx phi minus cj, yeah, in every index j. So again to replace exponential by this operator, differential operator. Then this is going to hit a. Remember, a is a symbol of order m, which means that it's not going to lower the order of a, but here we have the following. We have a homogeneous relation of order 1. This is of order 2. So every time we integrate by parts, we're going to bring this relation, relation at the power minus 1. Yeah? So every time we're going to have minus n. And this will help us to show this is rapidly decreasing because of homogeneity, dx phi minus c is actually bounded below by c plus theta. Okay, so from here we're going to have c to the power minus n, which means rapidly decreasing. Okay, so indeed the wavefront set of this kind of distribution is in lambda phi. We're going to use this later a lot. Now we continue with a little bit of symplectic geometry. So linear algebra, we're going to use a vector space equipped with the symplectic form omega. So this means that it's bilinear, linear in every slot. It's non-degenerate. For every u, there is a v such that omega is different than 0. Skew symmetric, and this is a form on v. This is necessarily even, and we'll see why. Dimension of v must be 2n if we have the symplectic form here. For example, the area form in R2, dx wedge dy. In R2n, we have the variables x and y, so then we have the sum of the area form in every index, dyj, dxj. And here, for your definition here, when you look at the vectors xy and x prime, y prime, this is exactly what omega does, 1/2 of this sum. Now, let's look at the subspaces of the symplectic vector space V. So we have omega here. We're going to define for the linear subspace L something like the orthogonal complement, but we don't have an inner product here, so we're going to use omega. So this is L omega, omega orthogonal of L, the set of all the points V such that omega of u v equal to 0. And we're going to use this L omega to define the following. L is isotropic if L is subspace of L omega, coisotropic if L omega is a subspace of L, and Lagrangian if they are equal. So now we have the Lagrangian appearing here, the Lagrangian which we need for the FIOs, L equals L omega. If we look at the formula here for the dimension, it means that the dimension of V is twice the dimension of L, which means that V must be even dimension, yeah? Dimension of V is 2 times dimension of L. That's why dimension of V is 2n. Some examples, any dimension 1 subspace is isotropic because omega of VV is 0. Codimension 1, it must be coisotropic. We're going to see a very nice proof here in lecture 3 using the Hamiltonian vector fields. It's simple with the Hamiltonian vector fields. In a dimension 2 space, any one-dimensional subspace is Lagrangian because it's isotropic and coisotropic. Other examples are R2n, Rn cross 0, or 0 cross Rn. Again, these are Lagrangians. Okay? Now we continue with manifolds. So we're going to introduce again, it was done yesterday, the cotangent bundle using the coordinates. So we have coordinates x1, x2, xn in x. This induces coordinates xu on the tangent space and xc on the cotangent space in the following way. If we have a point from the tangent space, a vector from the tangent space, then u is given by ui dxi. This is the basis. If we have a cotangent vector in the cotangent bundle, then xc is given by xi dxi. Again, this is the basis. We're going to use this to define the canonical 1 form, which is xc dx. The canonical 2 form, which we're going to use a lot, which is d sigma, which is dxc wedge dx. And again, I wrote here the definition for you. Oops, a definition for you. For omega, dxc wedge dx. This is bilinear, it's skew symmetric, non-degenerate, and closed because d omega equal to 0. Okay. So now we are in the symplectic manifold setting. So you consider a manifold, smooth manifold with a symplectic form, which is closed and differential 2 form, and becomes symplectic on the tangent space of M. And again, dimension of M is 2n. For example, T star Rn, Cn, T star x with omega defined before. So actually, any symplectic manifold looks like T star Rn. It's better to think about it like that, T star Rn. Also going to define the conic subspaces because we're going to work a lot with this with FIOs. gamma is conic in T star x if the point xc is in gamma, then the ray also is in gamma. The ray xtc is also in gamma. And our Lagrangians for the FIOs will be conic. For example, something which was mentioned yesterday and on Tuesday, if you consider psi dio with the principal symbol, the characteristic variety, the set of all the points where Pm is 0, is conic, yeah, because of homogeneity here, and is closed, is the inverse of the 0 point here. And now Lagrangian manifolds, we have seen Lagrangians in the vector spaces, now Lagrangians on the manifolds, symplectic manifolds. So you consider a symplectic manifold, a submanifold which is smooth. This is isotropic, coisotropic, or Lagrangian if the tangent space of L is isotropic, coisotropic, or Lagrangian in the tangent space of M. Okay? So the Lagrangian manifolds actually they are the intersection of the coisotropic and isotropic. But given a manifold, how do we check its Lagrangian? The easiest way is the following. We're going to check the dimension has to be 1/2 of the big dimension of the mother space dimension, and the omega should be vanishing on R. Yeah? So it's easier to check. That's how we check manifold is Lagrangian. So let's apply it for this example. If we have a C infinity function, let's look at the graph of df. This is a Lagrangian. It's not conic, yeah, because T is not here. We don't have the ray here. But why is this a Lagrangian? So look at the symplectic form, dxc wedge dx. This is our xc df. We have to look at dxc. And dxc wedge dx, actually, this is 0 if the second order derivatives are equal. F dxi dxj equals dxj dxi. Yeah? But it's exactly true because f is continuous, and Clairaut's theorem will tell us that these derivatives are equal. So omega vanishes here, so indeed this is a Lagrangian. But again, it's not conic. When f is 0, we have the 0 section, and again, it's Lagrangian, not conic. And we're going to say again, we said yesterday a lot of discussion yesterday about the 0 section. I think it's enough. The homogeneous microarc analysis works in T star x minus 0, okay? So we take out the 0 section. Okay, now we're going to define the canonical transformations. So we have two manifolds, symplectic manifolds of the same dimension. We have a smooth map. This is a canonical transformation if the pullback of omega n is omega m. Yeah? The omega n is the symplectic form on m, omega n is the symplectic form on n. And if this is the case, it's called a canonical transformation. The graph of this is a canonical graph. And this is a very nice, we'll see later, FIO, if it has a canonical graph, as a canonical relation, it's a very nice operator. It's very easy to work with. That's why I'm going to introduce it here. This is also fees at local diffeomorphism. If you look at the volume form, the determinant here will be different than 0. For example, if you consider any diffeomorphism from xn to yn, then this induces a canonical transformation phi from T star x to T star y in the following way: chi of x, and then you have the derivative, the inverse, and the transpose applied to xc to get from T star x to T star y. Okay? This is a canonical transformation given by any diffeomorphism. Okay, now I said this is a canonical graph, but actually there's another way to check it's a canonical graph, which is much easier, and it's going to come toward the end of this talk. If we have a Lagrangian, how do we know it's a canonical graph? We'll see exactly later. We don't have to find this phi, actually. And now let's see the relation between Lagrangians and the conormal bundles. So we defined the conormal bundles yesterday. The idea is that every conormal bundle is a conic Lagrangian. Okay? But the converse is not true. Not every Lagrangian is a conormal bundle. And let's see why. First of all, a very important theorem. Any Lagrangian can be macroarcally parametrized by a non-degenerate phase function. In other words, any Lagrangian conic looks like lambda phi. Again, lambda phi, x from the beginning, yeah? It's x dx phi such that d theta phi equal to 0. So any Lagrangian T star x can be parametrized by this phi, and any Lagrangian looks like this, okay? So why this is the case, we're going to use this a lot here. So we have a conic Lagrangian. We can always make a change in variables and assume that lambda has the form xc such that x equals dh dxc, where h is homogeneous of degree 1. So that's why lambda becomes conic. And then you consider the phase function phi of the form x dot xc minus h. And this is going to parameterize lambda, dx phi, x dx phi such that, actually this is xc, such that dxc equals to 0. It's exactly lambda. Now let's consider, in this setting, let's consider a special function h, homogeneous of degree 1, c1 cubed over c2 square. Okay? Now, if we write same phase function here, we look at the derivatives, and now we're going to show that lambda phi is actually a closure of the conormal bundle of the cubic. Without the 0 point, the smooth points parts of the cubic. So it's a closure of the conormal bundle. It's not a conormal bundle. It's a Lagrangian, but not a conormal bundle. Yeah? So this is one example. We'll see others, but this is one example that there are Lagrangians which are not conormal bundles. So now we are ready, using this symplectic geometry, we are ready to define the Fourier integral distributions. So we remember the setting. We have a phase function non-degenerate, x and theta. Phase variable, space variable. Then we have a critical set where d theta phi equal to 0. Then we look at h, the map from a critical set to t star x, h of x theta equals x dx phi. And we consider the image lambda phi x dx phi such that d theta phi equal to 0. Okay? So phi is given, we can find critical set, we can find x dx phi, and we can write this Lagrangian lambda phi. We're going to show that this is a conic Lagrangian. So it's conic because phi is homogeneous of degree 1, since it's a non-degenerate phase function. And it's Lagrangian because, let's look at this simple calculation, the one-dimensional, one canonical form is going to vanish on lambda phi. So remember, we define this as c dx, but c here is dx phi. So this is dx phi dx. Formally, this is the derivative, actually the differential in phi minus the derivative differential in theta. Now this is 0 on lambda phi. And d phi is also 0 because of the Euler homogeneity condition. Yeah? When you have a homogeneous function of degree 1, phi is sum of theta I d theta I. So this vanishes on lambda phi, which means that the second form, which is d sigma, also vanishes here, which means that lambda phi is a Lagrangian, okay? And it has dimension n, and conic also. So now, with this phase function, we're going to form this set of distributions into the I phi. So again, non-degenerate. A is a symbol of 1, 0 here. We're going to talk about this order in a minute. Integral over Rn. And these are Fourier integral distributions. The wavefront set is lambda phi. We said this, it's a local conic Lagrangian. And Im of x and theta is the set of all these locally finite sums. For any Lagrangian here, we have lots of phase functions parameterized as lambda, so we consider all these finite sums of these distributions. So what happens with this order here? It's a Hormander formula, and it's something we learn it by heart, yeah, if you do macroanalysis with the FIOs. So we have M, the order of the class, then we have the dimension of x, yeah, over 4, dimension of theta over 2. Okay? So this was set up such that when we have psi DOs, you have to remember this, for the psi DOs, this M is exactly like this M. Okay? Now, for the composition calculus of FIO, so transverse condition, we'll see this in the third lecture. Because of this symbol, under the transverse intersection condition, the orders add up, M1 plus M2. Okay? When it's a clean intersection, it's a bit different. So it's a reason why it's here, but the truth is that we use it, we learn it, and that's what we use it. So we have these Fourier integral distributions. Again, what do we need? A non-degenerate phase function and a nice symbol. And then lambda phi is the wavefront set of U phi, conic Lagrangian. We're going to see examples now, and these are the examples you have seen yesterday, and Alan introduced them yesterday. For example, a conormal distribution. Every conormal distribution is a Fourier integral distribution. Okay, so now we have lots of examples here. Let's see why. So again, the same setting. Let's check the definition. Let's check the wavefront set. So we have y, we have codimension k, we have the conormal distribution. We have seen it yesterday. The phase function is special phase function. Why is this non-degenerate? Well, it is homogeneous of degree 1 in theta. Yeah. D phi, we could do all the calculations here is different than 0. And then the derivatives with respect to theta are giving us phi j. So the differentials are linear dependent, these are linear, since these are defining functions. So this is non-degenerate. Yeah? This phi is non-degenerate. Symbol is the nice symbol as M10. Let's compute the lambda phi using the same formula. It's like a recipe. X dx phi is this, such that d theta phi equal to 0, which means that x belongs to y. This is exactly the conormal bundle of y. Okay? So this lambda phi becomes exactly the conormal bundle, which you expect, and we have seen this yesterday. So any conormal distribution, it's a free integral distribution. Other distributions, well, all these are conormal. So let's review, because we're going to work a lot with this today. Let's review the operators from yesterday. Yeah, the first slides from yesterday, they are online. You can look over them. Psi dios, the kernels are conormal distributions, x minus y dot theta. The pullback by chi of x minus y, this is undegenerate. The Radon transform, integral over the hyperplanes, y dot omega minus s. Spherical mean, x minus y length equals t, okay? And the Mello-Stello transform, again, we have here this conormal distribution, okay? These are all conormal, yeah, you can see they're all linear. There's one more, T6, but we're going to talk about this later, okay? So you've seen this yesterday. And it's good to check, if you want, that they are non-degenerate phase functions, okay? And the lambda phi will give us exactly the conormal bundle. And now we're going to talk about the invariance of phase function a little bit here, but it comes more in lecture 3. So I said that any Lagrangian, for a special Lagrangian, we have lots of phase functions parameterized in the Lagrangian. If we have two of them, phi and phi tilde, we can always go from one to another using a chain of transformations. So what can we do? What we usually do, we can add variables. So for example, if phi depends of x and theta, if it's a phase function which parameterizes lambda, I'm going to add the variable sigma square over theta to make it homogeneous of degree 1. This is also non-degenerate and parameterizes the same Lagrangian. Okay, so now we have the variables theta and sigma and as phase variables. Or we can reduce variables, stationary phase. Everybody knows stationary phase? Okay, so you're familiar with it, yeah, stationary phase, good. For example, if I start from here, I'm going to reduce sigma because the Hessian here is different than 1, there's 0. So we can do, and from these variables we go to phi of x theta. Or a change of variable, which actually we do a lot. Going to change of variables, so phi tilde is x of theta tilde of x theta. And here I do the calculation for you. Critical set of phi tilde is the same as critical set of phi, yeah, because the theta phi is 0. Lambda phi tilde, again, is going to be lambda phi, and the distributions here are the same. So there are ways, yeah, to go from one phase function to another phase function using this kind of operations. And we do it a lot, especially stationary phase, because we don't want to work with too many variables, but if it's possible, we do it a lot. Okay, so now we are ready to introduce the Fourier integral operators. So now we're going to transfer everything from Fourier integral distributions to the product space, and we're going to get the Fourier integral operators. Okay, so very similar ideas, but now in the product space. T star x cross T star y. Okay, these are the operators of the analysis. So on T star of x cross y, it's natural to have the natural symplectic form with the sum. But if we look at T star x cross T star y, we have the natural symplectic form with the minus. So actually we're going to define a very nice conic Lagrangian in the product space with the minus as a canonical relation. So C, T star x again minus 0 times cross T star y minus 0 with the minus relation here. This is a conic Lagrangian, and this is called the canonical relation. Now, if I put a minus here, C prime, the twisted canonical relation, actually it's a Lagrangian with the plus, yeah, because I put a minus here. And it was a nice explanation yesterday from Maciek talk, what happens with this minus here using the psi dios, yeah, if you remember. So having a conic Lagrangian, we are going to define the Fourier integral operators. So these are operators with this canonical relation whose kernels are Fourier integral distributions on the product space. Okay? So operator, the kernel, it's Fourier integral distribution, which we have seen before, but in the product space, Im of x cross y with the canonical relation C prime. Okay? So now we can transfer everything in the product space. We're going to denote by Im of x, y, and c such a class of FIOs with the order M and canonical relation C. So again, we remember now we are in the product space, a conic Lagrangian, which we have seen before. So let's see again calculation here. We want this oscillatory form. In lots of applications, we need the oscillatory form. We need the phase function here. Again, non-degenerate, same definition I've seen before. A, same kind of symbol, yeah, 1, 0. Only that here we have dimension of x plus dimension of y, yeah. So before we have x, now we have x, y of space variables, and then we have theta again in Rn. So we have a little bit of different formula here, but it's very similar. We have the canonical relation, which is lambda phi. So what is lambda phi in the product space? very similar. X dx phi, y dy phi such d theta phi equal to 0. Same recipe. The derivative with respect to x and y such d theta phi equal to 0. We put a minus here. Yeah, we talked about this before. So now let's see again examples. We're going to revisit our examples from the beginning, from yesterday, and show them that they are FIOs. That's why we started with them yesterday, examples of FIOs. A side U, it's an FIO. Yeah, it has a very simple phase function, which is x minus y dot theta, and this is the graph of the identity. Then the pullback. Let's look at the canonical relation, x dx phi, y dy phi such d theta phi equal to 0. It's exactly what we have. Radon transform omega s, the derivative with respect to omega and s, y, the derivative of y, such that d theta equal to 0. Spherical mean operator, again, the derivative with respect to x, with respect to y, such that d theta phi equal to 0. Melrose transform, same derivatives here. Again, it's a nice exercise to look at these canonical relations and take the derivatives. And the half-wave operator here, which was introduced yesterday, which is in these books also. I make it easier here. I consider x minus y plus t p times theta. Yeah, this is the phase function. Yesterday we have phi of x, y, theta. If we consider t fixed, the canonical relation here is x theta, y theta, minus dyp, okay? And this is Fourier integral distribution in the product space, but it's node conormal. Okay, another example of node conormal because the phase function is not linear. Okay, but it is a Fourier integral distribution. So every conormal distribution is Fourier integral distribution, but Fourier integral distributions, they may not be conormal, like this one, the halfway operator. Okay, so now we go deeper into the analysis of the FIOs. So remember FIOs, product space, canonical relation, Lagrangians, conic, then we have phi non-degenerate, and a nice symbol. Okay, this is what we need for an FIO. But now we're going to apply them, we're going to use them, we're going to see a better analysis of them. Yeah, we know the phase function, but what do we do with them? So we start with C. Since it's a subset, a submanifold of the product space, it makes sense to look at the projection to the left and to the right, pi L and pi R. And we're going to consider these projections as mapped between sets of the same dimension or different dimension. And we're going to study these projections. So let's look at the dimensions here. C has a dimension nx plus ny, dimension of t star x 2nx, dimension of t star y 2ny. Okay? It is known that if one projection drops rank, so does the other one. They drop rank over the same set. In other words, the co-rank of d pi L equals the co-rank of d pi R. If one doesn't drop rank, the other one doesn't drop rank either. Okay? So we're going to look at the case in this lecture, but in the afternoon, after the lunch, you'll see a more complicated case. We're going to look at the case where the projections don't drop rank. So we're going to call the canonical relation a non-degenerate canonical relation if the projections have a maximal rank everywhere. Yeah? They don't drop rank. So if you have a different equal dimension between x and y, they don't drop rank. So there are maps between sets of dimension 2n and 2n. They don't drop rank. They are local diffeomorphism. And then C becomes a local canonical graph. So this is what I told you before. If we have a manifold with the projections, with the maximal rank and the dimensions are equal, this is a local canonical graph. So we don't need to find that phi. It's just enough to look at the projections. So much easier to look at the projections to the left and to the right. It's so much easier to look at their differentials, and if they don't drop rank, then we are fine. But if the dimensions are different, for example, x greater than y, then if they don't drop rank, it means that pi L is an immersion and pi R is a submersion. Okay? Here, I'm going to introduce a condition called the Borker condition, which is very important in inverse problems. We'll see why in this talk and then a little bit in the next talk. So we are still in the setting of non-degenerate setting. If pi L is also injective, then we say that F satisfies this Borker condition, and it's very important again for inverse problems. So, okay, let's look at some canonical relations and projections. Okay, because again, I said that's very important. We'll see later, yeah, when you go to inverse problems, it's very important to understand these canonical relations and their projections. The Radon transform, again, the phase function here, the canonical relation, which you have seen before. Let's look at the coordinates here. We have omega, we have y, we have theta, so C3 has dimension 2n. And then we project to left and right. Again, they have 2n dimension and 2n dimension. This is our projection pi and pi r. So let's see what kind of projections we have. And we look, it's enough to look at one of them, which one is the simplest, and find the rank of d pi r. For example, this is the easiest one. Rank of d pi r. Well, since we have here the identity in y, this doesn't matter, yeah, for the rank. Then we look at what's left, eta, in respect to theta and omega. So this is the derivative, yeah, the Jacobian, d eta, d omega theta. And this is also non-degenerate. So the rank here is 2n. It's a maximal rank, which means that pi r is the local diffeomorphism. So is pi l, which means that C is a canonical graph, okay? The canonical relation of the Raluca transform is a local canonical graph. They are non-degenerate projections. It's not global canonical graph because pi r is 2 to 1 here, okay? Because if we take the points minus theta minus omega, we obtain the same thing. So it's a local canonical graph. But it's good enough for estimates and inversion and so on. The Radon transform. Another one, the spherical mean operator. The calculations, so C4 looks like that, but these calculations are in the first lecture. Yeah, I think they were a little bit rushed yesterday, but you have them in the notes. So for the spherical mean operator, we have this canonical relation. Again, projections left and right, xc and t star x, and then y eta, but again, it's this xc, x minus t, c over xc and xc. And here it's very simple to see that they are they are actually diffeomorphisms, both of them. And this is a full canonical graph, yeah? C4 is a canonical graph, okay? Again, we don't need to find that function phi. Another one is something like a half-wave operator type, the wave equation. So if we consider the wave equation, I didn't write it here, but we all know it, with initial conditions and with the Fourier transform. If we do this, then we're going to have this phase function in the solution plus minus here, okay? So just consider the plus. Yeah, for the wave equation, everybody recognizes this. For this phase function, homogeneous of degree 1, let's compute the canonical relation. So we have the variables xt in one side, y in the other side, derivatives with respect to y, with respect to x and t, derivative with respect to theta, projections. And what happens here, I put this example here because we have different dimensions here. So before we have dimension 2n, everything has the same dimension, but here they're different. So C has dimension 2n plus 1. And here, pi l goes from 2n plus 1 to 2n plus 2, and pi r from 2n plus 1 to 2n. Okay? So they have maximal rank. It's easy to see. So we have an immersion and a submersion, which is also 1-to-1 here. Okay? This is one example of a canonical relation with the projections between sets of different examples. Again, non-degenerate because they have the maximal rank. Okay, so we have seen some examples. We look at the projections. Again, it's very important for inverse problems is coming. What do we do with FIOs? We do estimates and we do composition calculus. So there are lots of estimates known. Today, only the ones for the non-degenerate case, but there are lots of degenerate cases for which the estimates are done. So degenerate cases means that the projections drop rank. Okay? So let's look at the theorem by Hormander. If we have a non-degenerate canonical relation, then f of order m maps hs to hs minus m. But here it's an adjustment of the order. Yeah? That's why we want to have a nice loss here, s minus m. So we have to write the order m minus the absolute value delta dx minus dy over 4. Yeah? If we have a psi do, or if dx and dy are equal, then this doesn't matter. Fm is the same. So let's apply this theorem to our examples. For Radon transform, we have a canonical graph. So then dx and dy are the same. This is the order of the Radon transform. So T3 maps hs to hs plus n minus 1 over 2. Same for the spherical means. T4 maps hs to hs plus n minus 1 over 2. Okay, equal dimensions. But for the wave equation, we have a difference of dimension. Yeah, we said there the difference is 1. So here we're going to have m minus 1 over 4, yeah, the difference of dimension. But this operator has order minus 1 over 4. If you want to write this in the form m minus 1 over 4, m is 0. So then T maps hs to hs. Okay, everything is local here. Okay, so we have this kind of estimates for non-degenerate case. We have others for degenerate cases. Yeah, lots of examples. It's from x to y. Ah, okay, okay.
No, it should be x2.
Yeah. X, y, y, from y to x?
I see.
Ah, okay. Okay, that's right. Okay, so we've seen estimates for non-degenerate case. Now let's see composition calculus. Very little, because it's coming in the third lecture. But let's see why we need composition calculus. So this is a motivation also why do we study FIOs. They come in inverse problems, lots of inverse problems. I'm going to look only at the seismic case, a little bit of seismic case, but also they come a lot in radar imaging and other inverse problems. So the idea is the following. We have an inverse problem in the following way. We have a source at the surface, which emits acoustic waves to the subsurface. There's a scattering here of the heterogeneities. They are the differences between different edges between materials, sand and rock. Then there's refraction. And then at the Earth, the surface, we measure the pressure field, and this is our data from which we find the image of the subsurface. So we know all the time the Fourier operator, which maps the image to the data. The model here, mathematical model, is the wave equation. We have P, the pressure field, and C is the velocity field without the direction. We solve this, Green's function. The problem is that P depends of C highly non-linearly. So it's hard to find C from P. So we're going to linearize in the following way. We're going to consider that C is a perturbation of a smooth known background velocity field C0. To C0 corresponds P0. We know this. So P becomes P0 plus delta P. We put all this in the wave equation, and we have a new equation here with delta C, delta P. And we consider a new Fourier operator from delta C to delta P, and we're going to restrict to the time, it's a finite time, and the set of receivers and sources. This is our new linearized Fourier operator, delta C to delta P. So you want to find the image, This maps the image to the data. I want to find the image. What kind of operator is this, and what do we do to find the image? Well, it is known for a long time ago that F is an FIO, result of Rakesh. To find the image, you use the back projection operator F star. So you have to look at F star F, and this is the composition of FIOs. F is an FIO. So is F star. I didn't say this, but it's coming in lecture 3. When F is an FIO, so is the joint. So you have to look at F star F. We like this very much to be the identity to find the image, but it's not all the time. It's not many times. So you have to look at composition of FIOs, F star composition F. If we have the Boca condition, then this is IDO, a very nice operator, and this, when this is elliptic, can be inverted if we have the Boca condition. In the seismology, the Boca condition means travel time objectivity condition. It's the same thing, that's how they call it. But if this is not satisfied, and this is the case many times, it's not satisfied. In other words, if you have caustics in those rays, then F star F becomes very wild. And from here, we have these open problems and new problems for studying FIOs, When this condition is not satisfied, what can you say about F star F? And there are results, so far known, but not many, but there are results. So what does it mean acoustic? We look at the map from the source, let's say point source, the time, to the subsurface point. If this map has 4 singularities, then we have a 4 caustic. Again, we're going to talk more about this in the lecture 3. 4 singularities means folds like a parabola. Okay? When we have 4 singularities, it means that the projection, also both of them are degenerate, and they have 4 singularities. So they don't have maximum rank anymore. The projections to the left and the right, they have these singularities. And we call C a two-sided fold, and we look at the CT composition C because we want to study F star F. In this case, there's no Boca condition here. We look at CT composition C, and we get 2 images of the image, actually, 2 location of the image. The diagonal, which is the good one, and another one, which we understand, it's another canonical relation, which is another two-sided fold, which is called an artifact here, because there are 2 locations. One is fake, one is good, from the inverse problem point of view, but how do we distinguish between them? Now, this kind of calculation was done by Meadows and Taylor before, so this was known for the two-sided fold. So, as I said, there's no Boca condition. What can you say about F star F? Well, we're going to see in lecture 3 that F star F, when F is a FIO of order M with this kind of canonical relation, degenerate canonical relation, we see that F star F, it's a new operator. It's not FIO. It's not side U. It's a new operator whose kernel is in an IPL class. And I'm going to define this in lecture 3. It's a very nice class, introduced by Günther and Melrose and Gilman, and then my advisor later, Greenleaf. It's an IPL class, 2 orders here, 2 Lagrangians intersect cleanly. It's a very nice class, and it is something, a new result about the composition calculus F star F. Because when you compose two FIOs, you do not obtain always an FIO. So there's the beauty here. And I mean, it's not easy, but this will give us open problems to look at the composition calculus. What can we say about the composition of two FIOs under certain conditions? And there are several results about these operators F star F. Okay? So we summarize. We have FIOs. We have canonical relations, like conic Lagrangians, always in the product space. We have projections. We have seen projections. We have degenerate case, non-degenerate case. We look at estimates. That's what we do with FIOs. We look at estimates. And we look at composition calculus. Okay? And this is like a little bit of introduction in the next lecture about FIOs, and we'll see exactly the composition calculus and other estimates and other definitions and a little bit new results, which are not in these books. So, okay, that's it. No, not FIO. No, it's another operator. It's not SIDO, it's not FIO. It's another operator whose kernel belongs to a new class of distributions, IPL class of delta and C1. Yeah, because when you compose F star and F here, we have this one. We have 2 Lagrangians. Delta and C1, we don't have 1, To be an FIO, we need 1. We have 2 of them, and we understand them. They are Lagrangians which intersect in a special way, intersect cleanly, and there is a class of distributions which is associated with this kind of Lagrangians.
But locally, away from the intersection, there are FIOs. If you remove this,
Yeah, but it's not easy to remove. Yes, away from this, it's an FIO on delta and FIO on C1. But in inverse problem, it's not easy to remove the intersection. And they are there, I mean, okay? Especially if you consider all the data, you will have both of them. And also they are not disjoint, because then you can write them as a sum, but they're not disjoint, they intersect cleanly at some point. So that's why you have to consider this class of IPL classes.
Any other questions?
So this funny formula for the order of Lagrangian distribution, this is chosen so that when you change the number of theta variables, it's consistent with how the symbol.
Where?
Yeah, it's back.
For FIOs, this one?
Yeah. This is. I'm just trying to understand the numerology.
Sorry. So we have M, the order of the operator.
This is M plus the dimension X.
Dimension of X plus Y, because in the Crowder space, but if it's it can be only X, if we are Fourier integral distribution. Minus the dimension of theta, N over 2.
Yeah, I understand. This is consistent if I change the number of theta variables.
Yeah, it's the same. If you reduce?
Right, because the order of the symbol will
be different.
You said it's stationary theta, so.
Yeah, so it'll be different, so then M changes. Usually what you do, you know the order of the symbol and you find the order of the operator. So you start in the other way, okay? Using the same thing, dimension of X plus dimension of Y and dimension of theta.